Hey, honors physics students. Here are several problems regarding electricity and the solutions. And I'm going to go through them pretty quickly so I can stay within the 10-minute YouTube delineation. So anytime you want, you can push pause to try to understand this more. I will also upload this as a PDF file to Edline. Anyway, here goes. So one of the main formulas for electrostatics is that if you have charges and the electrons are going to repel one another, or the charges will attract or repel, here's the force formula that we use. F equals K Q1 Q2 over R squared. The K is a constant, always stays the same. But the Q1 is charge number 1, Q2 is charge number 2. Well, in this case, the force starts out to be 1 Newton when the distance is 1 meter. Now notice, if the charges are shortened in distance to 1/4 meter, the force is going to be larger, but how much larger? Well, the new force will have no change in the constant, or Q1 or Q2, but the new distance is 1/4 where it used to be 1. Well, you know the 1/4 is in the denominator and it's squared, so that becomes 1/16. Now you know that when you divide something by 1/16, that's the same as multiplying by 16. So you're basically taking the original KQ1, Q2 over R squared, which was 1 Newton, and multiplying by 16. So the force went from 1 Newton up to 16 Newtons. When sugar is poured in a bowl, you may have seen that sometimes the grains scatter. They scatter because of the force between the charges. By friction, the grains have been charged. And so this is simply plug the numbers in. The constant is 9 times 10 to the 9th. The charges are the same, so 3 times 10 to the negative 11th coulombs is then squared. Remember, the way you put these into the calculator is the times 10 to the is the E button. So you do second function comma for the times 10 to the. Then you have to square the denominator. This gives you a force of 0.0013 newtons. That would be repelling the charges. Number 3 is a different kind of problem. Okay, so for number 3, then we talk about a heater having current. Now, current is the letter I. It's the number of electrons that flow per second. And the voltage of the line is 110. So just like we've done from the beginning of the year, use knowns and unknowns. If I know the voltage and the current, the formula power has VI, and you'll get 2,200 watts. We get charged at our house for the kilowatt hours. So divide this by 1,000, you get 2.2 kilowatts. If you multiply 2.2 kilowatts times 10 hours, according to E equals power times time, you will be using 22 kilowatt hours of energy at a rate of 10 cents a kilowatt hour. That's $2.20 that it costs to run that. We'd like the resistance of 120 volts. And I apologize. So the power supply is 120 volts, but this is a little bit of a typo. This should be 120 watts of power. So the power then is V times I, but I equals power over V. 120 over 120 is 1 amp. So 1 amp will go through that lamp. So the resistance for Ohm's law, R equals V over I, 120 over 1. That's 120 ohms for the resistance. Number 5. So now we have circuits. The rest of these will be circuits. This is a series circuit, meaning the electrons from the battery, every one goes through every resistor. It's a series circuit. So when you solve a series circuit, the first thing you should do is find the resistance of all of them and just add them together. The 15, 10, and 6 make 31. Ohm's law for the whole circuit, the current coming from the battery, is the total voltage divided by the total resistance. 10 over 31 is 0.32 amps. That's the current in every single spot in the battery and each resistor in a series circuit. This is a tougher question because it's a series parallel combination. So first of all, we would like to make this into one resistor. What the electrons do is they split up here. Some of them go to the 15 ohm resistor, some to the 10. So first I do the 1 over R for the equivalent resistance or the total resistance of the parallel is 1 over 15 plus 1 over 10. On my calculator, I would add these, then take the reciprocal, and I get 6 ohms. That means this entire parallel combination is the same as a 6 ohm resistor. We now have a series of a 6 and a 6 makes 12. Current for the whole circuit is V over R, 32 over 12 make 2.7 amps. That's the current coming from the battery. It would be different in each one of these, as you'll see in number 7. Again, same thing to start out this problem. We have a series circuit of an 8 ohm resistor, and then it branches to a 30 and a 20. So the first thing is the current in the parallel branch is 1 over 30, 1 over 20. Add those on the calculator, reciprocal it, and then you get 12 ohms. So this is the same as a 12 ohm resistor. The total circuit resistance would be the 8 plus the pretend 12 makes 20 ohms. That's part A. Part B would be the current coming from the battery in the circuit. That's the total voltage over the total resistance for Ohm's law. And for that, you get 60 over 20, 3 amps. That's 3 amps coming from the battery, 3 amps in this resistor, but it splits up unevenly because the resistances aren't the same. So for part C, to find the voltage in this one, every electron goes through here. So that means the current is 3 amps from the battery and 3 amps in the 8 ohm resistor. Then multiply it by just the resistance of that and you get 24 volts. Notice, of the 60, you lose 24 volts here, meaning you'll have 36 volts to lose whichever way you go here. We can find that in part D by using the voltage for the parallel branch is, now you could pretend it's a single 12 ohm resistor times 3 amps, gives the 36 volts that I just mentioned. Then the current for just one single resistor, like the 20 ohm resistor, would be the 36 volts you get for that resistor, divided by the 20 ohms for the individual resistor, 1.8 amps. Of the original 3, you'll have 1.8 going this way. That means you have 1.2 going this way. That should complete this. Hope it helps you on the other electrical problems.